So today I will be solving chemical energetics question from A2 level. This is the paper. This is 2016 paper, May June, variant 4.3. All right. Predict the sign of standard enthalpy change for this reaction. Explain your answer. Right. This is one of the most standard question you will face in your exam. So let's start by figuring out the particles. Alright, so in the reactants we have 2 moles of gas. 2 moles of gas, and over here 1 mole. So in total we have 3 moles of gas. Over here we have 1 mole of gas and 4 mole of gas. That makes total of 5 mole of gas. So standard entropy change is, we know that standard entropy change is entropy of products minus entropy of reactants, right? So we have more moles in our products, so entropy will be positive. Now we have to explain why. It's because you see there are more moles of gas particles in the products. All right. The free energy change for this reaction at 1000 Kelvin is 51 kilojoule per mole. Calculate the value of enthalpy change for the station stating its unit. Right. So for the Gibbs free energy, the equation states Gibbs free energy is equals to enthalpy change of reaction minus temperature and entropy change. So we are given the enthalpy change and Gibbs free energy is 51 kilojoule. Alright, over here I would like you to notice one thing. Our entropy is in general given in joule, and our Gibbs free energy and reactions are given in kilojoule. So we have to take it into joule. So our so we'll just take the answers in kilojoule, right? We'll just keep it kilojoule over here. So I'll be using 51. Entropy is enthalpy is 241 minus temperature is 1000 and this. All right, let's put it out. We have 241 minus 51 divided by 1000. It will give us 0.19. Right, this is our magnitude. Now we have to find out the unit. We'll write kilojoule mole minus 1 K minus 1. Now this is pretty much a memorization, you have to know this, but if you want to derive, you can do it. How? Let me show you. You found it as Gibbs free energy, reaction minus temperature and entropy, right? So our entropy is enthalpy change minus Gibbs free energy over temperature. So actually their units are kg, kilojoule, mole minus 1, and temperature is Kelvin. That's why it becomes kilojoule mole minus 1 Kelvin minus 1. Now you have to understand that when you are subtracting or adding any two units or any two values, the unit remains the same. When you are multiplying meter into meter, it becomes meter square. But whenever you are multiplying meter plus meter, it gives meter. Right, that's for physics. Let's turn chemistry for now. Now third question, how would the value of G and hence the spontaneity of this reaction changes as the temperature increases? Alright, so we already know that enthalpy change of reaction is 241 kilojoule. That is a positive value. It's the endothermic reaction. And our Gibbs-free reaction states that change of enthalpy change minus temperature and entropy change. Let's say that the react temperature increases, right? So if a temperature increases, enthalpy change minus temperature and entropy change. All right, we have found that the entropy change is a positive value. So if we increase temperature, or this part becomes more negative. As a result, our Gibbs free energy becomes more negative. So what we'll write? We don't need to write the answer. We'll just write T minus. Sorry, my bad. We will write negative T. Entropy change becomes more negative. Hence, Gibbs free energy also becomes more negative or exothermic. You can write whatever you want in between these two. Exothermic, hence spontaneity increases. So in this video, I'll be solving the chemical energetics questions from 2016 year. So let's just go through the few more questions we have left, and I'll be trying to solve the question as a student, as how I will solve the papers if I were to give the exam. I mean, I'll be sitting for the exam. So yeah, let's start. Chromal chloride CaCl2 can be prepared by heating a mixture of potassium dichromate and potassium chloride with concentrated sulfuric acid. Alright, that's the equation over there. Use the following data to complete the Hess's law cycle and calculate the enthalpy change of the reaction del HR. Right. So they pretty much given us everything we need over here. And as you know, if all formation are given, there's a shortcut for your answering. That is, if formation given, we'll just write the formation of products minus reactants. That's the privilege we are getting there. Alright, let's draw the cycle. We know from elements products are forming. We'll just draw an arrow. Alright, that's a mistake. We'll draw an arrow. Over here we'll also draw an arrow. That's it. And let's write the values. To form 2CrO2Cl2, it's 2 minus 580, and plus we have 3K2SO4, K2SO4, 3 minus 1438 plus 3 water, that's 3 minus 286. Right. Then over here we have K2O7, that's 2061. Then 4 CaCl, that is 4 CaCl minus 437 plus sulfuric acid 3 minus 814. Alright, you know, just for helping, we'll just write del H1, del H2. This for like just a simple help. We don't need to write it. So you see the cycle is like this. So these are from here, from elements we'll go over this final product, but the cycle can also follow in this direction. But whatever the cause, we will use our law that we learned, product minus reactant. So del HR is listed that 2 minus 580, it's a must you write, plus 3 1438 plus 3 1286 minus for reactants we have 2061 plus 4 minus 437 plus 3 minus 814, and it will give a value of minus, let me put it in calculator. Alright, it's 81 kilojoule per mole. Alright, minus 81.0. Just I'll add a 0 for I like it. Now this might be the last question. Alright, it's quite a big one. Let's see. Calcium metal reacts with chlorine gas to form calcium chloride. Write an equation including state symbols to represent the lattice energy of calcium chloride. Right, we have to present the lattice energy. So the equation we have for lattice energy, alright, we need to mark few things. First we have to ask the lattice energy. The lattice energy, from what do we get the lattice energy? Lattice energy, what do we understand by lattice energy? When 1 mole of ionic solid is formed, 1 mole of ionic solid is formed its elements, right? From its elements in gaseous state, right? This is mandatory in gaseous state. So what we will write is the elements in the gaseous state, right? So we have calcium chloride, we have calcium 2 plus in gas plus 2Cl minus in gas, giving us calcium chloride, right, which is a solid. And the solid is a must because it's saying that it's ionic solid. Complete a fully leveled bond have a cycle that could be used to calculate the lattice energy for the calcium chloride. Now, right, let's do it. Right. So we'll try to use the fully leveled diagram. We'll try to write everything that we can. It's the 2 marks. Let's give it a shot. So we have to understand one thing. Again, is ultimately we're coming to an ionic solid. So we'll be needing calcium in its calcium. Alright, we need calcium in its gaseous state, chlorine also in its gaseous state. How can we get that? So calcium, let's see, calcium is a solid. We need to turn it to calcium in a first gas, because without being gas we can't make it into a gaseous ion. So after that we'll do ionization energy, which will give us calcium plus gas. Second ionization energy should give us calcium 2 plus and also gas mole. For chlorine, we have chlorine 2. So we have to, in a gas mode, we have to convert it into chlorine gaseous atom. Then we'll give it 2 electrons to make it negative ion, gaseous ion, right? There's electron affinity through. Right now, let's start writing the answer. This is our starting point of our equation. So at first, we'll convert calcium solid. Then we'll be converting the chlorine to gaseous atom. It's a gas, 1 mole of gas, 1 mole of gaseous chlorine. That means we have a chlorine gas that's of 1 mole. We are converting into it 2 moles of gaseous atom of chlorine. That is 2Cl gas. For that, we need twice the atomization of chlorine 2. Right. Alright, my bad. We don't write chlorine 2, we just write chlorine, right? We're doing atomization of chlorine. Because what do you understand by atomization, right? Alright, here's the tip. Why 2 mole? Atomization is creating one mole of gaseous atom from its elements, right? So we have a chlorine bond. We'll be breaking that bond to get 1 chlorine gaseous atom. If we are to get that, we have to have the bond energy to get 1 chlorine. But since we want 2 chlorine over here, we need to multiply 2. That means 2 atomization, because we're getting 2. It's like the standard enthalpy change, right? Those who knew, alright. Those who didn't knew, you should get a firm grips, gaps of it. I'm tripping, bro. Alright. Then we are done with chlorine. Now let's deal with calcium. First, we'll turn calcium solid to calcium gas plus 2Cl gas. There's atomization of calcium. Then we'll convert it into calcium plus gas plus 2Cl gas plus electron. You don't need to add the electron, but I just like it to be there. It's in bracket, so they won't cut mark if you don't add it. Here's first electron affinity, ionization energy, first ionization energy of calcium. Then finally we are with our calcium 2 plus a gas, 2Cl a gas, and 2E minus. That's our second ionization of calcium. Now here's the catch. In Born-Haber cycle, there are two vertical lines, here and here. So one will always be going up and one will always be going down. So you have to consider one going right, my bad, I'm tripping. So yeah, one will be going up and one will be coming down to the product we want. So you have to count either one as positive, other one as negative. So if you count the upper cycle as positive, all the values, you have to take the lower ones negative. Now you also have to understand that since our atomization, we need the energy, it's a positive value. Atomization is a positive value. Ionization, we're removing electron, so we need to provide energy to remove the electron. Yeah, that's also a positive value, that's also a positive value. But here, the electron affinities, as you can see, is given a negative value for the chlorine atoms. So obviously it will have a negative value over here. Formation is also negative. So you say that the line, vertical line is going downwards will be considered negative, and the line that is going vertical is positive. And you will see the all the energy values that's going up is equal to all the energy values that's coming down. So your net enthalpy change will be 0. That's what Hess's cycle states. Alright, now let's back to original answer. From here, we need to turn this chlorine to an ionic gas. We will write calcium 2 plus gas, and we have 2Cl minus gas. Don't have the electrons now because the chlorines have taken the electrons. Alright, over here, so it will be 2 electron affinity of chlorine. Is the first electron affinity. And finally, we have our enthalpy change of lattice. One more is of lattice. Alright, we done our Born-Haber cycle. There's a booklet to answer. So from the booklet, we'll only need values for ionization, and here I will write values for my help. The atomization of chlorine. With atomization of chlorine, right? It's half the bond energy. That is 2 half chlorine bond energy, right? We'll look for CaCl bond. There's 2 for 2. Then atomization of calcium, there's given as 178. First ionization of chlorine. Alright, go to the ionization energies, look for calcium. Alright, I have gotten calcium. The first ionization is 590, second one is 1150, Now coming back to our electron affinity is -3 to 9, so I'll write 2 minus 3 4 9, and formation is -796. All right, let's start. So to the value for lattice, actually I want you to write the values, because there's the catch over here. You need to write the what's happening in the equation. That will help the teacher for marking, right? So I'll just write the ones that going up and the ones that coming down. So it's 2 atomization of chlorine plus atomization of calcium plus first ionization energy, second ionization energy is equal to enthalpy change of formation, and enthalpy change of formation plus enthalpy change of lattice and 2EA. Alright, let's put the values. We have 212, 242, and it's 178, 590, 1150. Formation we have 796 plus, alright, we don't know the lattice, we'll just keep it, plus is 2 minus 349. Alright, there's a little error over here. The thing I wrote, alright, it will be like, let me show you guys, wait. Here we go. So from this over here, one of the reaction is coming, the formation takes place in this direction, right? And if there is a direct reaction, there's another alternate pathway that goes like this. So there are two directions. So we can say our formation, enthalpy change of formation is equals to chlorine so formation 796 let me put that in calculator. 242, 178, 590, 1150. Just close. Alright. This is a measure of disorder of a system. Describe what happens to the entropy of a gas when the temperature is increased. Interesting question. That's the common question. Alright, so we should know that as temperature increased, right? What happens to gas particles when temperature increases? So when temperature increases, they gain kinetic energy, so they move faster. And so entropy will increase, right? Alright, let's start writing. Entropy will increase. Why? because gas particles gain kinetic energy, gain more energy. Okay, right. Gain more energy. Right? Let's gain more energy, and move randomly. Alright. Tables force the reactions. We have to predict the sign of the entropy change. Right. So let's judge. We have 1 mole of gas, 2 moles of gas, 1 mole of gas. It's negative because it's product minus reactant, so it's negative. Reaction will not happen. So we have half mole of gas and 0 mole of gas. So it's negative. And there's negative. Right, and as you can see there are copper sulfate and water, solid forms, right? Solid forms, so it's also negative, because you see in water they can move randomly, right? In water the copper sulfate can move randomly from one place to another, and can arrange itself in different parts, but copper sulfate is a solid, so it's a fixed position. Alright, over here there are a lot of ions. Alright, and we have gas. We have more ions, even gas, even liquids. So it's a positive, right? Because they can arrange themselves more, man. Isn't it the entropy change of the first reaction is negative? Because more gas in the product, more gas in reactant than in product. So we have to find the standard entropies. Simple, standard product minus entropy of reactions. So products is 2 ammonia, 2 in my band, it's 2 ammonia, 2 ammonia minus 3 hydrogen minus 192, and it should give a value of, let me put it in the calculator, minus 199. Damn, that's really random. And now I have to find the standard Gibbs frequency energy. That's a given, bro. The values are given, so we don't have to take care of anything. We'll just write the formula that will fetch us the mark. And we will take care of the units. So then so the 117, there's in kilojoule, temperature is 298, and our entropy is 175, and make sure to divide it by 10 to the minus 3, because we want it in same units. So we'll have 117 minus 298, 175, 10 to the power 64.9, 64.9. Alright, now this is an interesting question, because as you can see that this free energy is positive, hence not visible. Alright, and we are done with our 2026 paper. I'll be solving 2027 on a later video. Stay tuned.